let's talk about this ALU instruction code. When it is 1 on the first bit, then it is ALU instruction. And for the second to fourth bits, it connects to the bit selector of the ALU. For the fifth and sixth bits, it is for register A, and for the last 2 bits, it is for register B. In reality, it may delay a bit the clock signal when the wire is long enough, hence, when you OR gate the clock beat, and the delayed clock beat, it is for the clock enable, and the intersected part of both clock beats is the clock set. In this software, clock beat is independent of the length of the wire, so we can ignore the clock E and clock S for this circuit. Register B enable, register B set, register A, later will be used for the connection, thus we just leave there first. Since if the first bit is 1, it will trigger the ALU instruction operation, hence it is definitely needed to put as the input for all the AND gates to prevent the non-ALU instruction triggered it. The next 3 bits all connect to the ALU bit selector. The stepper in step 4 will release the data of register B and set it into the temporary register. After that, the stepper in step 5 will turn on the ALU bit selector and enable the register A to load its data to the input A of ALU, and meanwhile, the temporary register loads its data to the input B of the ALU so that the ALU can do its operation on that time. For the third input of the AND gate in step 6, its purpose is to avoid 111 operation to enable it, because 111 operation in ALU does not do anything as the design in ALU. The stepper in step 6 will enable the accumulator to load the data back to register B to store the data. Here is the final wiring connection when adding to this ALU instruction. For this add operation, I insert the 5 into R0 as the register A, and insert the 6 into R1 as the register B, and finally it will result as 11 because 5 plus 6 is equal to 11. Now ACC output will load back the result to register B. Right now let's do some other operation to prove this is working well. For the second operation we are going to do the shift right operation, which is shift right the 5, so the shift right result should be 2. As a result, it is 2 on the ACC output. For the last operation, I am going to show the OR operation when the R0 is loaded with 0.5 and R1 is loaded with 0A, so the final result should be 0F. As we reach the conclusion of this video, I would greatly appreciate it if you could express your appreciation by giving it a thumbs up. Thank you for your support.